Hey everybody, welcome back to differential equations and more on Euler equations. That we're going to look at another example of an Euler equation that we solve using the method of undetermined coefficients. Recognize that it is an Euler equation because the power of x that appears before the derivative is the same as the order of the derivative. X squared, x to the second power, second derivative of y, x to the first power, first derivative of y, x to the 0 power, which is 1, and the 0th derivative of y, or just y itself. This is another example. We're going to again illustrate the technique of method of undetermined coefficients for Euler equations. And our first step find the complementary solution. And the complementary solution is just this thing with the right-hand side set to 0. Now, if you look back in your notes from a day or two ago, we've seen this before. This was also the complementary equation in our previous example. Our previous example had the same complementary equation. So we're not going to go through the motions to get this again. We'll just note that we already know what the complementary equation is and focus on getting the particular equation. Particular, I beg your pardon, not particular equation, but particular solution. When we have a polynomial on the right side of our Euler equation, and we're doing the method of undetermined coefficients. We assume that our particular solution is a polynomial that has exactly the same powers of x that are found on the right-hand side of our original equation. So what does this mean? Let's take a look. We have a power of x to the, we have a power of x raised to the fifth in our original equation. So we'll say ax to the fifth is part of our particular solution. On the right side of the original equation, we have x raised to the power of 2. So we'll assume we have a power of x to the 2 in our particular solution. And we have x to the first power in the original equation. We'll assume that we have x to the first power in our solution. So this is what our particular solution should look like. We just need to find A, B, and C. And to do that, we'll find the first derivative and the second derivative. And we'll plug these into the original equation. X squared y double prime minus xy prime minus 3y equals x to the fifth plus 4x squared plus 3x. We've already decided that we know what yp, the particular solution, looks like. Now we'll compute the first derivative and the second derivative also, and plug those into this equation to solve for the constants a, b, and c. Again, particular solution is ax to the fifth plus bx squared plus cx. So y prime will be 5ax to the fourth plus 2bx plus c. And y double prime is going to be 20ax cubed plus 2b. And we're going to plug these three things into this equation. So we have x squared times y double prime. So we put y double prime here, 20ax cubed plus 2b. And again, that is our y double prime. Then we have minus x y prime And for y prime, we plug this in, 5ax to the fourth plus 2bx plus c. So there's our y prime. And then we also have minus 3y. And y is ax fifth plus bx x squared plus cx. And all of that should equal x to the fifth plus 4x squared plus 3x. And if I get my head out of the way, maybe you can see that. Okay, I think I've plugged everything in correctly. Now we just need to tidy things up a bit. And we have x squared times 20x cubed is 20ax to the fifth. I'm going to keep my ax to the fifth outside here. So I have x squared times x cubed is x to the fifth times 20a. And what do I have here? Negative x times x to the fourth is x to the fifth. Negative 5a x to the fifth. And then over here I have minus 3ax to the fifth. Okay, now let's see, what else do I have? I have x squared times 2b. So I have 2 times x squared times b. What do I have here? X times 2bx is 2bx squared. So I have another 2 here. And here I have minus 3bx squared. Okay. And let me just check this. X squared times x cubed, 20ax to the fifth, 20ax to the fifth. X squared times 2b is 2bx squared. That looks right. Negative x times x to the fourth is negative x to the fifth times 5a. Negative 5ax to the fifth, okay. Negative x times negative 2bx is negative, watch it right here, this was a mistake, negative 2 bx squared. Negative x times negative 2bx is negative 2bx squared. Oh, I'm glad I caught that now and not 20 minutes from now. And negative 3 times bx squared, negative 3bx squared. So far, I think we're looking okay. And I have no x terms here. I do have an x term here, though. I have minus cx. So I'll put minus 1 and cx here. And I have minus 3cx here. And all of that equals whatever our original right-hand side was. X, let's see, x to the 5th plus 4x squared plus 3x. Okay. (20 minus 5 is 15, minus 3 is 12. Ax to the 5th (2 minus 2 is 0, minus 3 is negative 3bx squared). Okay, negative 3bx squared. And negative 1 minus 3 is negative 4cx. And that equals this mess. X to the 5th plus 4x squared plus 3x. We have a polynomial on the left equal to a polynomial on the right. The only way that two polynomials can be equal to one another is if coefficients of like terms are equal. So that means the coefficient of x to the 5th has to be the same in both places. This guy has to be equal to 1. So 12a equals 1. And so a equals 1/12. Now, what else can we equate here? Terms of second degree. The coefficient of x squared on the left has to be exactly the same as the coefficient of x squared on the right. So that means negative 3b is equal to 4, or b equals negative 4/3. And then we can compare the coefficients of x to the 1st. Negative 4c has to be equal to 3. So we'll set those equal. Negative 4c equals 3, and that means c equals negative 3/4. Oops. Okay, there's our particular solution using the values of A, B, and C that we solved for. So let's finish this up. Our general solution we take the particular plus the complementary. So particular 1/12x to the 5th minus 4/3 x squared minus 3/4 x. So there's the particular solution. And our complementary solution, that was C1 x to the negative 1 plus C2 x cubed. Excellent. Problem solved. Oh, it can't always be this easy. Okay. Sometimes we do hit a bump in the road, and for those times when we do, we want to be prepared to deal with them. This was a problem that we had to deal with when we had linear differential equations with constant coefficients. It's a problem that we have to deal with when we have Euler equations. We handled this similarly to the case when we have constant coefficients and we have a repeated root. With constant coefficients, if we have a double root, then we'll have C1 e to the mx and C2 e to the mx. And these are pretty much the same thing. The fact that we have different constants out front doesn't change the fact that these two things are not independent of one another. M is the root of the auxiliary equation in each case. So if we have a double root and M appears as a root twice, we're going to get two solutions, but they're not going to be independent of one another. They're pretty much going to be the same solution. So to get the second independent solution when we have constant coefficients, what did we do? We multiplied by x. And this gave us the second independent solution. Now, when we have Euler equations, pretty much the same thing happens. Drum roll, please. Instead of multiplying the second solution by x, we multiply by natural log of x. Whoops. Constant coefficients. And I'm just going to put this up here for the sake of comparison. We have a double root and we get these two solutions, C1 e to the mx, C2 e to the mx, but they're the same solution. So we multiply the second by x. And we get C1 e to the mx and C2x e to the mx are our independent solutions. Can we read that? I hope so. we have a double root lambda, and that's going to give us c1x to the lambda plus c2x to the lambda. These are our solutions, but they're not independent. So we multiply the second by natural log of x. Not x, but natural log of x. Whoops. See, I did say not by x, didn't I? I did say not by x, but by natural log of x. So when we have Euler equations, we don't do this exactly the same way we do linear equations with constant coefficients, but the methods are similar. It's just that instead of multiplying by x to get that second independent term, we multiply by natural log of x to get that second independent term. Now, are we going to do an example showing what to do when we get a complementary equation that has a double root? Yeah, I think we should. Okay, what do we do first? Solve the related complementary equation. And the assumption is that our solutions all look like x to the power of lambda. So if y equals x to the power of lambda, then y prime is lambda x to the lambda minus 1. And y double prime is lambda times lambda minus 1 x to the lambda minus 2. And we can simplify that. See, this will be lambda squared minus lambda x to the lambda minus 2. So we plug these into the complementary equation for second derivative, first derivative, and y. And then we solve for lambda. What was our complementary equation? X squared y double prime. So here's x squared, and y double prime is this thing, lambda squared minus lambda x to the lambda minus 2. Okay. And then we have minus 9x y prime, so lambda x to the lambda minus 1. And plus 25y. Whoops, whoops, whoops. Whoops, whoops, whoops. Y is x to the lambda. Okay. It took me a couple of tries, but I finally got it. Well, I think that's right. Okay, x squared times x to the lambda minus 2, the exponents add, so we just get x to the lambda. Same thing here. X to the first times x to the lambda minus 1, the exponents add. 1 plus lambda minus 1 is just lambda. So we get 9 lambda x to the lambda. And 25 x to the lambda equals 0. And we're not interested in the case where x is 0. So we're assuming x is not 0, and we can divide both sides by x to the lambda. And I think this is going to give us our double root. I think this is x minus 5 squared. Or rather, excuse me, lambda minus 5 squared. Let's see, take the first and square it, that's lambda squared. Take the last and square it, that's 25. Take the first times the second minus 5 lambda and double it, minus 10 lambda. Yeah, that's it, all right. C1 x to the lambda and C2 x to the lambda. But these are the same. To get a second independent solution, I take this second thing and I multiply it by not x, but natural log of x. And this gives us two independent solutions. Are we done? No, we don't have a particular solution yet, so let's get one. This is our original equation. And since the right-hand side is a polynomial, we assume that the particular solution is also going to be a polynomial that has exactly these powers of x and no others. So we're going to have a power of x cubed, and we're going to have a term that has x to the first power. So let's say, call that bx. And this is x to the 0 power. So we'll just say c is our constant. And we'll compute first and second derivatives. going to take these and plug them into the original equation and solve for the constants A, B, and C. So let's see, we have x squared y double prime. So y double prime is 6ax. And then we have negative 9xy prime. And y prime is 3ax squared plus b. And then we have 25y. Y is ax cubed plus bx plus c. And that's supposed to equal this mess. I guess first I will look at all of my powers of a cubed. I have x squared times x is x cubed. So this is 6ax cubed. So we have 6ax cubed. Here, I'm going to get negative 27ax cubed. And then here, I'm going to get plus 25ax cubed. So I got my ax cubes all taken care of. Now I guess I'll look at my x's. I have bx here and bx here. Here I have negative 9bx. And here I have 25bx. Okay, I've got my x cubes and my x's taken care of. And I think, say 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5. Yep. This is my only constant term, 25c. the coefficients of x cubed have to be the same, and the coefficients of x have to be the same, and the constant coefficients have to be the same. So let's see. 6 plus 25 is 31, minus 27 is 4. So I have 4a equal to 4. Yipes, how did that happen? Well, let's hope all the others turn out to be just as nice. Let's see. Negative 9 plus 25 is 16b, and 16b equals 3. And so b equals 3/16. I hope. And let's see, the constant coefficients, 25c equals 2. So that means c equals 2/25. And our particular solution, let's see, what was it? Ax cubed. So a is 1. Oh, okay. So x cubed plus bx, 3/16x, plus some constant, c, 225. And there's our particular solution. We take the particular and the complementary solutions and add them together. So we have x cubed plus 3/16x plus 2/25. There's our particular solution. And I'm guessing c1x to the, this is where we had the double roots, wasn't it? So we had c1x to the 5th plus c2 natural log x to the 5th. Voila. We might be wondering about this. We might run into something this ugly, but it's only ugly if we don't know how to deal with it. Suppose that we have a triple root. What do we do then? Essentially, we do the same thing that we would do with a linear equation with constant coefficients. If we have m as a triple root, then to get our independent solutions, we have c1 e to the mx plus c2 x e to the mx plus c3 x squared e to the mx. We do the analogous thing with Euler equations. We have c1 x to the lambda. Now c2 times x to the lambda is not going to be independent of this solution. Essentially, they are the same solution. So to get an independent solution, we multiply this by natural log of x. Well, okay, but now what about the third solution? C3 x to the lambda. Well, we can multiply this by natural log of x, but then these two things are not independent. So we take the third solution and multiply it by natural log of x again. And now we get independent solutions. Well, is there anything else that can go wrong with the complementary solution? There is one more thing. This is only a nasty thing if we don't know how to deal with it. We had an analogous situation with linear differential equations with constant coefficients. And one thing that we noted was that if the complementary or auxiliary equation yielded complex roots, these complex roots would always appear in conjugate pairs. You never see one without the other. As long as we have complementary or auxiliary equations that have real constant coefficients. Any equation that's got real constant coefficients, if it has complex roots, those roots are going to appear in conjugate pairs. Okay, so here are our two imaginary numbers, and notice that the second is the conjugate of the first. They have the same real part, and the imaginary part of the second is just the negative of the imaginary part of the first. So essentially, we just took the sign in between and changed them from positive to negative or vice versa. Let me just put these together. C1 x to the lambda 1 plus C2 x to the lambda 2. And we look at this and we rightly say, what the heck are we supposed to do with this? Well, let's simplify it first. That we have x to the power of a sum, x to the power of a difference. We can write that as x to one power times x to another power, like this. We can say x to the a power times x to the bi power, and again x to the a power times x to the negative bi power. Oh, this looks good, I think. Now these two terms have a common factor, x to the a. We'll factor that out. And we have C1 x to the bi plus C2 x to the negative bi. And this kind of sort of looks like what we had with constant coefficients, except with constant coefficients, we had e to the bix and e to the negative bix, or maybe ibx. And we found out that with e to the power of imaginary numbers, this pair turned out to be a linear combination of sine and cosine of bx. Well, something similar happens if we have x to the power of bi and x to the power of negative bi. We get x to the a, some constant times cosine plus some constant b times sine of something. And here's what that something is. It's going to be natural log of little bx, natural log of little bx No, it's not either. I'm sorry. I am sorry. Natural log, I'm sorry, cosine of b natural log of the x, that looks much better. Sine of b natural log of x, oh, that looks so much better. And these are our two independent solutions. X to the a times this thing is one independent solution. X to the a times that thing is the other independent solution. Dare we do another exercise? Yeah, I think so. I think so. So find the solution to the related complementary equation. And that equation is this thing with the right-hand side set to 0. And we assume the solutions are of the form what? X to the lambda. for an Euler equation, that's the trick. So let's see, y equals x to the lambda, y prime is lambda x to the lambda minus 1. And y double prime is lambda minus 1, x to the lambda minus 2. And if we tidy that up a bit, lambda times lambda is lambda squared. Lambda times 1 is lambda. We're going to plug those guys into the complementary equation, and then we're going to solve for lambda. Our complementary equation was of the form x squared times y double prime. So that's y squared minus lambda x to the lambda minus 2. And then after that we had minus 5x times y prime. So that's lambda x to the lambda minus 1. And just as a reminder, y double prime, y prime. And then we had 13y. And y is x to the lambda. So did I do it right? Here's y. Here's y prime, goes there. Here's y double prime, goes there. I think I did it right. Now let's tidy this up a bit. X squared times x to the lambda minus 2, the exponents add, and we just get x to the lambda. So lambda squared minus lambda, x to the lambda. X to the first, x to the lambda minus 1, the exponents add. X to the first, x to the lambda minus 1, the exponents add. We just get x to the lambda. And then 13 x to the lambda is 0. Divide both sides by x to the lambda. I don't really see how to factor this, so I'm going to hit the chicken switch and use the quadratic formula. So negative b plus or minus square root of b squared minus 4ac all over 2a, and hopefully this will simplify. I have 6 plus or minus 36 minus, let's see, 4 times 10 is 40, 4 times 3 is 12, minus 52 over 2. Six plus or minus 4i over 2. So lambda equals 3 plus or minus 2i So we'll say lambda 1 equals 3 plus 2i. And lambda 2 is 3 minus 2i. So I plug in lambda 1 and lambda 2. X to the 3 plus 2i. X to the 3 minus 2i. Okay. And I'll split each of these two things up into the product of x to 2 powers. C1x cubed x to the 2i plus C2 x cubed x to the 2i. And I do that because I'll get a common factor of x cubed. And if we have, remember this, C1 x to the bi plus C2 x to the negative bi, that's going to be a cosine b natural log of x plus a sine b natural log of x. So that tells us exactly how we can rewrite this. X cubed a cosine 2 natural log of x plus b sine 2 natural log of x. And let me just tidy this up. x cubed a cosine natural log x squared plus b sine natural log x squared. And that's our complementary solution. I think that's what it looked like. Let me check. 3x squared plus 2x. We're going to assume that our particular solution looks like the right-hand side in this sense. The particular solution is going to have as powers of x exactly those powers of x that appear on the right. So y particular should equal ax squared plus plus bx. Y particular, ax squared plus bx. Y prime particular is 2ax plus b. And y double prime particular is 2a. And we're going to plug those into the original equation and solve for a and b. This is our original equation. So we'll have x squared, and then y double prime, which is 2a, x squared y double prime, and then we have negative 5x y prime, which is 2ax plus b. So there's our y prime. And then we have 13y, and y is ax squared plus bx So there's 13y. And all of that equals 3x squared plus 2x. Okay, let me tally up my x squareds, my ax squareds. I have 2ax squared, and here I have negative 10ax squared, and here I have 13ax squared. Okay, now let me tally up my x's. Let's say bx here. I have negative 5bx, and over here I have 13bx. And simplifying, let's see, this is 15 minus 10 is 5. And this is 13 minus 5 is 8. Very good. So 5a is going to be 3. And 8b is going to be 2. So I should have 5a equals 3, and so a is 3/5, and 8b is 2, so b is 1/4. So my particular solution is ax squared plus bx, where a is 3/5, and bx, where b is 1/4. That's my particular solution. Complementary. That was x cubed times something. A cosine natural log x squared plus b sine natural log x squared, I hope. Was that what it was? Yes, yes, yes. Okay. I have a few things left to show you about Euler equations, but I want to start you on some homework. For now, work on those. I have a few more things to show you as far as Euler equations go. But do these, get warmed up on these, and then when I give you a few more tidbits, you'll be ready to work the whole thing. And I will say this also, this lecture would not be a bad lecture to watch again and just work through the examples that we worked through in the lecture. Look at the exercises that we did. If you get stuck, go back in the lecture and look at how we did it. If you don't need to go back to the lecture and look, that's fine. But if you want to go back and check, that's good too. Work on these, work through them. If you get stuck, check the lecture. And then work these guys. And in a day or two, I will have the rest, the concluding chapter of Euler equations. Until that time, everybody, please stay healthy, exercise soundness of mind, and let's make this a productive semester. We still have plenty of time in the semester to do quite a bit in addition to what we've already done. And I mentioned something to my number theory class a couple of days ago, and my students said they really appreciated that because it was something that they didn't know and it was rather insightful. Right now, there are things that we can't do just because of the world situation. But don't worry about the things that we can't do. Let's just worry about the things that we can do. And this can be a very productive time in our academic career. Seriously. And just to back up that point, I cite the case of Isaac Newton. He invented calculus. He also discovered most of the laws about planetary motion and gravitational attraction between any two bodies. He was, well, without a doubt, the Einstein of his century. And of note is the fact that while he was at the university in London, a scourge of the bubonic plague hit England and hit London in particular. So to escape the plague, Isaac Newton retreated back to the family farm for a couple of years. And it was during these few years that he was in seclusion at the family farm that he made most of his scientific and mathematical discoveries. So Isaac Newton at one time was in very much the same situation that we're in now, and yet this turned out to be the most productive period of his life. So let's not worry about what we can't do. Let's just do the things that we can do and do them well, and make sure that we do have a fruitful semester. And I'm confident that we can do it. Stay safe and healthy.